Hello, folks. Today we are going to talk about electromagnetic induction. Okay, this is a very important phenomenon. There is so much that there is a law. Not just there is a law, a physics law associated with it, but there are lots of most of our electricity is obtained from electromagnetic induction. Okay, so where does the idea of electromagnetic induction comes from? How physicists start to look for something like that, and what does it mean? Okay, electromagnetic induction is exactly what the word means. Okay, electromagnetic induction is inducing an electric field from a magnetic field, or even better, inducing an electric field from a magnetic field, or even better, at the start, they didn't see that. They didn't see the electric field being induced by a magnetic field. Instead, what scientists saw before, we realized that was happening. Instead, inducing, or in other ways, right? Or in other ways, in other words, the induction of current by a magnetic field. Okay? Before electromagnetic induction was discovered and proven to exist, scientists initially start thinking about Ampere's law. Think about Ampere's law, right? Ampere's law states, that a current, an electric current, creates a magnetic field. And in science, there's a lot, there are lots of phenomena that we can take the other way as well. For instance, in this case, we say that the electric current creates a magnetic field. People, scientists start thinking whether a magnetic field could create an electric current as well. Okay? After discovering Ampere's law, that's what scientists start to think about. Is it possible that the other way around could also happen, right? Is it possible, right, that the other way around could also happen? And by other way around, what do we mean? Is it possible that a B field could also generate a current in a circuit? That's what the question, a current in a circuit, that's what, the question that scientists were asking themselves. Okay, and the answer that they got was quite surprising. Okay, magnetic field alone, have to be had to be a very specific characteristic, had to have a very specific characteristic to generate a current in the circuit. Okay, and it is at this point that I want to refer you to a video that I'm going to show to you. Okay, very soon. But what scientists discovered? What exactly scientists discovered? Scientists discovered that you could induce a current without a battery in 4 different ways. Okay, 4 different ways. By changing a magnetic field in time. Okay, one way to do that is by inserting a magnet, is by moving a magnet closer and further away from the loop. Okay, when you do that, the magnetic field of the magnet is going to change in time, because you are either approaching the magnet. What does it mean? It means the magnetic field is increasing. And then if you're removing the magnet, The magnetic field is decreasing. There is a change in the magnetic field as a function of time. That's what scientists discovered. I'm going to illustrate that right in here. Okay. Here you go. You have a current. There is no battery in the circuit whatsoever. Okay, and creating a current, you can create a current by providing a battery to the circuit, right? When you look at this circuit, we have an area vector that's pointing into the direction of my screen here, right? Now, if you add a magnetic field, remember, doesn't have to, this magnetic field must have a special characteristic, right? A magnetic field that is constant is not going to be able to induce a current. This magnetic field has to vary in time. So when you have something like that, a varying magnetic field, you can induce a current. And the current is going to be either clockwise or counterclockwise depending how the magnetic field changes. Okay, this is real life. This happens in real life. And let me show you another example, okay, of a changing magnetic field in time. Okay, get a coil, a solenoid with lots of wires wrapped around it, and you put a ammeter in this circuit. Get a magnetic bar and approach it towards the solenoid. If you do something like that, the magnetic field from the magnetic bar is going to change and it's going to induce a current here in the circuit. Okay, that's the first way to generate a magnetic field. Going back here. So what about the second way? The second way is also illustrated. Here you go. In this case, you must have a change of magnetic field in time. And here too, you can have a change in magnetic field in time, of the magnetic field in time, okay? And what's the second way of doing the same thing? Of inducing a current, that's what you call law of induction, right? So suppose that we have our circuit that has no battery whatsoever, and we have this other circuit with a battery. The difference is that the circuit is open and there is no current flowing through this circuit. You close the switch and the current builds up from 0 to a given value in a very small amount of time. Because the current is building up with time, the magnetic field associated with this current is also going to change as time goes by. So in this very amount of time that the current grows up and then stabilizes, you're going to see an induced current here in this circuit that again has no battery whatsoever. Whether you close the circuit or you open the circuit. Okay? So the second way again involves a change in magnetic field. The third way, you don't have to have a change in magnetic field. Okay, so going back here to the notes. Instead of, you can have a constant magnetic field, just like I have here, but something else must change. And this something else is the area of the circuit. Think about the circuit expanding and contracting, like a rubber band, right? Like a circular rubber band. Suppose you could do something like that. So the magnetic field does not have necessarily to change in time, doesn't have to change in time necessarily. But the area of the circuit, yeah, if the area of the circuit changes, you get an induced current. Okay? Another way, then that's the most important one, because that's the one that provides us with electricity. Another way to induce a current, is by getting that same circuit with no battery. I'm going to emphasize that. The magnetic field is constant as well, it doesn't change in time, but now you go ahead, put an axis in there and put the circuit to rotate. Okay? If you do something like that, you will induce a current as well. And by the way, most of the electricity that you will get from the utility company use this type of device, this configuration that you see right here. Very simple. Okay? So having said that, 4 different ways. And by the way, that was the experimental evidence that scientists had back in the 1800s. Okay? There is a YouTube video that we can watch as well. I'm putting that here for you to watch, that describe the historical background. Okay, I want you to take a look. And strictly speaking, so what's happening? If you change the magnetic field, you get an induced current. If you change the area of the circuit, you get an induced current. If you get the circuit to rotate with respect to the magnetic field, you also get an induced current. So what's exactly going on here? Okay, the key understanding, scientists realizes that in reality, what you need to change, what you need to do to induce a current was to change not the magnetic field, but you have to change something else called the magnetic flux. Okay? By the same token that we have an electric flux, we also have a magnetic flux. And the magnetic flux, as you remember, here you go, just like the electric flux, the magnetic flux is going to be given by, something that involves an integral. It's not a closed area, but that's why I didn't put the circle there inside. But is B, what else? B dot, in this specific case, dA. Okay, that's what the magnetic flux is all about. Recall that the electric flux is E dot dA, right? Infinitesimal. And if the magnetic flux changes in time, then you will have an induced current or an induced electromotive force. That's the key idea that was discovered. It's a law in physics, a very important law, and I have spelled that out right in here. And by the way, there is this negative sign that we're going to discuss here in more detail. Okay? And what this epsilon represents is an electromotive force. Okay, I prefer to represent that by the letter V, but many books put it like as an epsilon. It's a type of voltage. It's a type of electric potential, not exactly the same that we have for electrostatic, but it's a type of electric potential. So we can induce an electric potential difference and consequently power a current. In ohmic circuits, okay, in an ohmic circuit that has ohmic elements, this equation for V reduces to the well-known Ohm's law, R times I. Okay, so think about that, and let's think what's going to be the consequence of that. Here's a demonstration. Here's a demonstration of electromagnetic induction. Okay, let's take a look at this video. I'm gonna post that in my notes.
On this page are demonstrations of electromagnetic induction, which is the generation of an electric field by a changing magnetic field. In these 2 videos, I was moving a magnet into and out of the center of a coil to generate a current in the coil. A viewer inquired as to what would happen if I moved the magnet laterally to or along the outside of the coil. This video demonstrates and explains what happens. Here is a bar magnet with a north and south pole. Running inside the magnet will be lines of magnetic flux density field, which will then emanate outside the magnet. Here is an illustration of those lines of magnetic flux density. So they'll emanate out the north pole and around the magnet and then back in the south pole. And you can see that the spacing between the magnetic flux density field lines will decrease as you move away from the magnet, indicating a reduction in strength of the magnetic flux density field. Here I have a galvanometer, and I have it connected to a 100-turn coil.
Okay, this coil has no battery whatsoever. The only thing that he did was to connect it to a multimeter. Not a multimeter, but a galvanometer, a ammeter, okay? Notice that there is no battery whatsoever.
So whenever there's a changing magnetic flux with respect to time inside the coil, there will be an electric field generated, and that electric field inside the coil will result in a current flow. So when I take this bar magnet and move it towards the coil, there's an increase in magnetic flux with respect to time, and I see a positive current generated. Now when I remove the magnet, there's a decrease in magnetic flux with respect to time, so I have a current flowing in the opposite direction. And the current that's generated is proportional to the rate of change of magnetic flux with respect to time. So I move the magnet slow, I get a small current. If I move it fast, I get a larger current flowing. I was asked the question, what would happen if instead of moving the magnet into and out of the coil, I was instead moving it around outside the coil? Well, as long as I'm moving the magnet, I am getting a change in magnetic flux with respect to time inside the coil. It's just that that change in magnetic flux with respect to time will be small because the magnetic flux density field falls off with distance from the magnet. But if you watch closely, when I'm moving it lateral to the coil, you can see a little bit of movement of the needle indicating I am generating some current. Similarly, if I'm moving it alongside the coil like this, again, I'm getting some change in magnetic flux with respect to time, and you can see a little bit of movement of that needle indicating a little bit of current being generated. Now, the current generated is going to be proportional to the change in flux linkage with respect to time, which is the product of the change in magnetic flux inside the coil and the number of turns of the coil. So if I greatly increase the number of...
Very, very important. If you do this experiment, it's just a single loop, you will barely see the needle moving here. However, if you put several loops here like this one, then you're gonna get a more perceptible change in the flow of the current. Okay.
Turns of the coil, then when I move the magnet outside the coil, I should be able to generate much more current. So here's a coil I wound that consists of 30,000 turns. So for the same changing magnetic flux inside the coil here, I'm going to get a much greater change in flux linkage. So let me now connect this 30,000 turn coil to the galvanometer. So now even when I move the magnet slowly, I generate current because of the large change in flux linkage with respect to time. So I have to be careful not to move it too fast and damage my galvanometer. Okay, so now let me move the magnet laterally. So you see there was a current generated because there was a changing magnetic flux inside the coil. So as I'm moving it towards the coil, there's an increase in magnetic flux, and I was generating a positive current. Now, as I continue to move the magnet and away from the coil, now there's a decrease in magnetic flux inside the coil and a negative current generated. So now I'm going to take the magnet and move it alongside the coil. So as I'm moving it towards the coil, I noticed I was generating a positive current, and as it continues to move away, now it's a negative current. So as I'm moving it towards the coil, I'm generating an increase in magnetic flux and a positive current flow, and now as it's moving away, I have a decrease in magnetic flux and hence a current flowing in the opposite direction.
So I'm posting here the link for that video that you saw on YouTube. It's a nice demonstration. There are more videos like that you can explore. And let's go back to the questions now, right? So let's take a look here at the Faraday's law, right in here. Electric potential, electromotive force is equal to the variation of the magnetic flux, derivative of the magnetic flux with time. And the magnetic flux depends on what? Depends on the magnetic field, depends on the area of the circuit, and also depend on the orientation of the magnetic field and the area vector. The minus sign here has a very important interpretation. Okay, the minus sign in there states what's the direction that the field is going to flow. What's the direction that the current is going to flow? Okay, and this formula that you see here is just for one single loop of current of circuit. So if you have n loops, so this value must be multiplied by n, right? And then the electromotive force gets amplified by that. Okay, going back. Okay, so that's the law that you have to memorize. Okay, and now let's write that down, right? All the laws we learned so far, and then you can continue. Here you go. So let's go to these laws that we have here, right? Start memorizing them, right? So the first one is Coulomb's law, or even better, Gauss's law. Is Coulomb's law in an integral format. The second law is this one that you see here. See, they both have a dot product between the fields and the area, right? The difference is that the magnetic field doesn't have a source, a radial source for the field itself. What you see here is Ampere's law that we covered, and now we have this new law here. This new law can be written in a different way, right? Remember that this epsilon that you see there is an electromotive force. And being an electromotive force, we also have another way of writing this law. How would you be doing that? We would be, recall that the electric potential, right? We must have an electric field right in here, which is also a line integral, in which we write our law. So by the same token that a changing magnetic flux can induce an electric potential or an electromotive force, it also can induce a current, right? And I'm even going to put an induced current. But strictly speaking, it's not electric potential that this guy is generating. Strictly speaking, it's not a current either. Strictly speaking, what is generating, what it's creating is an electric field. And by the way, yeah, and then we can leave this way. So now we have all our 4 equations of electricity and magnetism. Let's do a quick example of how we can quantify this law, right? A numerical example of this law. So we have a coil with 200 turns of wire. The coil is a square. D is 0.18, right? And subject to an external magnetic field perpendicular to the plane of the coil, which increases linearly from 0 to 0.5 in 0.8 seconds. It's a linear increase. What's the magnitude of the induced electromotive force or the voltage? Okay, we're going to do that. Here we go. The B, is increasing from 0 to 0.5 in 0.8 seconds, right? So we should have a constant, a proportionality constant here times a t. The B starts at 0, time t equal to 0 is 0, because it's turned off, right? But it keeps on increasing linearly at this rate, 0.5 Tesla per 0.8 seconds. And that's the equation that we end up having. The B field is perpendicular to the plane, what means that it's parallel to the vector area of the coil. Okay, so the electromotive force is going to be the number of turns multiplied to the change of magnetic flux. Okay, because the B field is uniform, we do not need that integral, but let's keep this integral there anyway. Okay, so B is, and also the B field is perpendicular to the plane of the coil, consequently is parallel to the vector area. This B dot dA is going to become B dA. We can put the variation of the magnetic field right here in this equation. And don't forget we still have this derivative, right? Take the t out of the 0.625 Tesla per second t out of the integral, and we are left with this integral of the area, which, by the way, we know this 0.8 meters times 0.8 meters. Okay, and then at this point we go ahead and do the calculation, and what do we get? We get this value here for the electromotive force, 4.05 meters squared Tesla per second, which ends up being 4 volts, 4.05 volts. That's a good example. Okay. And we can repeat for another one in which the magnetic field varies exponentially, like we have here. And then we go ahead and perform all the mathematical procedure, right? We don't even need the integral because the magnetic field doesn't change with the position. It just changes with time. It's a uniform magnetic field, but it's not constant. And we get something like that as well, that decreases exponentially. Okay. So we have here another example of motional EMF. Think about two rails in which a train moves through it, and a conducting bar that's moving with a given velocity. So what's happening here? And also we have a magnetic field that's pointing into the paper, into the plane of the screen, right? So what's happening here? We have this circuit. Oh, we have a resistor here at this end, and we have this circuit right here. As this bar moves, you're going to increase the area of the circuit, and you're going to change the magnetic flux. Here the circuit is not closed. Here the circuit is open. Okay? So, picture a train pulling a conducting bar along the rail it travels, right? The conducting bar is being pulled at speed v. Somewhere along the rail, you have some devices that require an electric current or a resistor. The resistor pictured in the figure. What do we need to find? Find the induced electromotive force first, then the electric current and the direction of the electric current. Okay? So let's do that together. Okay, so here we go. We have that the induced electromotive force is going to be the derivative of the magnetic flux with respect to time, ddt. The B is uniform, consequently can be taken out of the integral. The A can also be solved as being outside, taking out of the integral, and I wrote that down as being dA naught plus LVT. We have an initial area, right? An initial area. We have L here and VT. As the bar is pulled to the right, the area increases. The area is a function of time. We put it right here in this integral, and LV dt. LV can be taken out of the integral. Integral of dt is going to be t alone. dt is going to be 1, and we get BLB. That's what the electromotive force ends up being. And then we can plug in the numbers to get 10 to minus 3 volts. What would be the current? Okay, if you use a resistor, an ohmic element, like the resistor is, we can find out what the electric current is. I is going to be BLV over R. Okay, and finally, what about the direction of the current? The direction of the current we found out using what we call Lenz's law. Lenz's law is already implicit in Faraday's law. That negative sign that you see in Faraday's law, let's take a look again. The negative sign that you see in Faraday's law, this very negative sign here, is what Lenz's law is all about. And how do you determine, right? How do you determine the direction? How do you determine the direction of the current? Well, by using Lenz's law, right? Which is the negative sign in Faraday's law. This is a real law, okay? It's not a fake one. Okay, the negative in Faraday's law, the negative sign in Faraday's law means the following. The negative sign in Faraday's law means the following. 1. The induced current will flow in a direction opposite to that of the change in the magnetic flux. That's what you have to know. What does it mean? You know, if the flux increases, okay, the induced current will flow in a direction to counter the external magnetic field. On the other hand, on the other hand, if the flux decreases, okay, the induced current will flow in a direction to reinforce the external magnetic field. Let's work on that. Now let's come up with an example. Okay, Let's come up with an example here. Okay, so here you go. I'm going to let's start with this illustration right in here. Okay, this illustration right in here. Suppose that B is increasing, right? And the magnetic, if B is increasing, the magnetic flux is increasing as well. Let's see. Is increasing, okay. In this case here, no, suppose that the field is decreasing, okay? Suppose that the field is decreasing, dB dt, dB dt less than 0. Suppose that the field is decreasing. That's the case in which the field is decreasing, okay? So the induced current is gonna flow in such a direction as to create a magnetic field that's gonna reinforce my external field. So all I am doing here, you have to do the right-hand rule. If in order to reinforce the magnetic field, the current must flow in the clockwise direction to point in the same direction as the external magnetic field. Okay? Now, if the magnetic flux or magnetic field is increasing, it's all the way around. The current would flow in the counterclockwise direction. The field associated with the induced current must point against the external field. That's what you have to know. Once you understand that, you can find out what is the direction of the field. Here's a better way of illustrating that induced current, okay? So we have here my field, my circuit that's subjected to a magnetic field, to a uniform magnetic field. Let's start from scratch, right? Just the circuit. And we have the uniform magnetic field that's changing, that's increasing as time goes by. I call this black arrows the external magnetic field. So how do we find out the proper direction of the induced current? First, understand that this field, the external field, is increasing. Because the external field is increasing, then any magnetic field associated with the induced current must counter this external magnetic field, and that's what I have here. An induced magnetic field pointing in the direction contrary to that of the external magnetic field. And now, once you know the direction of the induced magnetic field, you can find out that the induced current is going to flow in the clockwise direction. Okay? It works for the other way as well. Negative, external field is decreasing. induced magnetic field correlated with the induced current must point in the same direction as the external magnetic field, and that's going to be the direction of the induced current. That's Lenz's law. We can do the same for that one. Magnet at rest, nothing happens, right? But if you move the magnet, you're going to induce the current. Now let us play with Lenz's law with that example that I showed to you, right? We have a rail, two rails here. We have a bar, conducting bar, that's sliding over this rail, and I attach a resistor there at the end. Not only that, we have a magnetic field. We have that this circuit is subjected to a magnetic field. Okay, let's put the bar here, and I'm going to get this vector right here, right in here. And now we have the magnetic field. Notice that this area that you see here is increasing, right? So it means that the magnetic flux is also increasing. Because the magnetic flux is increasing, the magnetic field associated with the induced current must counter the external magnetic field. And then you do the right-hand rule, and you get that induced current. The direction of the induced current would be in the counterclockwise direction. Okay, I have been telling you that everything that you get there is an induced electric potential, right? Induced current. But in reality, I mentioned there at the beginning that what you have in reality is not an induced current, it's not an induced electric potential difference or induced electromotive force, but what in reality you have, it is an induced electric field that's powering all that current that we observe. Okay, the way it works is like that. Here you go, you have this magnetic field and this circuit made of conducting wire. Okay, if the magnetic field changes in time, and let's say the magnetic field is greater than zero, the change in magnetic field is greater than zero, right? So what is going to happen here is that what this magnetic field is doing, it is inducing an electric field that's powering our current. So that's the actual field that's producing all that movement in electric charge, okay, in this circuit. And the electric field that is going to circulate around those magnetic field lines in this circuit. So let's summarize here. So that's what we have here. The change in B field actually induces an electric field in space that powers the current in the circuit. You can find out the direction of the electric field just by doing the Lenz's law, just by applying the Lenz's law as well. So in that example that we have here, because in this example that we have here, because the magnetic field is increasing, the electric field must rotate in such a direction as to counter the external magnetic field. So that's the guy that's really doing the job here in powering the current, the induced electric field. Okay, that's what scientists first saw, right? They were using conducting wires to measure current flow in the circuit. But if you throw away this conducting wire, in reality what's going to happen is that you're going to have electric fields there in space, circulating around the magnetic field lines. And we can even determine what's going to be the electric field, the induced electric field in this specific case, okay? So Here's an example in a qualitative fashion, okay? Consider a solenoid carrying a current in the counterclockwise direction. This solenoid is producing a magnetic field that points towards you on the inside of the solenoid, and the magnetic field outside the solenoid is going to be negligible. Now what do? We introduce a time variation in the current. Make the current vary in time. If the current is going to vary in time, the magnetic field is going to be proportional to this current. Let me clarify that this current is not an induced current, but it's a current that's being produced by a generator. Okay? And the magnetic field inside is going to be, a function of time. And what's going to happen outside the solenoid, right? What's going to be, for instance, the electric field outside the solenoid? Because this problem has, symmetry, magnetic field lines here are uniform, although it is changing as time goes by, and also we have circular symmetry, we should expect that we are going to have a electric field that's going to circulate around here in this position, okay? They're going to be like that. The direction of the electric field is going to depend whether the magnetic field is increasing or not. In the case of increasing magnetic field, the electric field circulates in the opposite direction as the magnetic field. And we can come up with, and what about inside? Inside we have something similar to, okay? You're going to have an electric field that's going to circulate as well, and because of the symmetry of the problem, the magnitude of those vectors induced electric field, they're going to be the same. The magnitude of this electric field is going to be the same as this one, and this one. Okay, and so let's do a more quantitative treatment of this problem. Okay, here you go. Consider a solenoid of radius r and n turns per unit of length. It has a time varying current that varies just like that. It's possible to produce a current like that. The current changes as time goes by. Determine what the magnitude of the induced electric field inside and outside the solenoid. Okay, so we have to start with that equation that you saw before. What I'm going to do separately here, let's see. Here you go. So what do we do? Draw the cross section of the solenoid. You already saw this drawing there, right? But now we are going to do in a more quantitative fashion. What you saw before was a more qualitative solution. Okay, direction of the magnetic field is going to be this one. And let us first solve this problem for r greater than big R. This is the solenoid of radius big R. This problem has cylindrical symmetry. And here you go. Remember that Faraday's law involves a line integral. This means that the E field will circulate around the region of varying magnetic flux. Every time, I'm going to write that down here for you, okay, in the notes. Every time that you see a line integral like the one below, what does it mean? It means that the field inside this integral, this line integral, will circulate around the term that is on the right side of the equation. Okay, that's what it means. And so we have this equation. Okay, let's not forget that is you have n right in here. You know, because the problem has, let's write that down here. Okay, I'm going to formulate here in the notes. Okay, as example, let a solenoid of radius r, right, and n turns per unit of length carrying a time varying current with the following format. Find the magnitude of the induced electric field, okay, inside and outside the solenoid. Okay, so our starting point is this one, and we go back to our drawings that we saw before. Here you go. Uniform magnetic field here, right? And we started with the electric field on the outside of the solenoid. Okay, because of the symmetry of the problem, right? Because of the symmetry of the problem, the magnitude, because of symmetry of the problem, we can choose a circular path around the solenoid, just like we saw. This is the circular path that I mentioned to you. Okay. Also, because of the circular symmetry, we can state that the magnitude of the electric field, magnitude of the E field, is going to be constant. One more thing that we have to do, is to choose the direction of the path It's going to be the same, right? It's going to be the same everywhere along the path. To choose the direction of the path, dl, direction of the infinitesimal path, dl. Note, see, okay, that both E and dl are tangent to the circle. Okay. Choosing a dl direction parallel to the E field instead of antiparallel, right? We can simplify our integral, our left side integral, or the E dot dl becomes E dl because they are parallel to each other. Because the E field has the same magnitude along the circle, along the circular path, right? Chosen, then we must take E outside the path integral, or what we end up here becomes like that. What you see here is the magnitude of E, right? We're still not working on this one yet. Hang in there. And finally, what's going to be the dl along the circular path? The dl along the circular path is going to be just 2 pi r. Okay, that was the left side of the integral that we have. What about the right side here of this equation? The right side of this equation is not difficult to calculate, okay? We already know that the magnetic field of a solenoid is going to be what? It's going to be, magnetic fields are always proportional to the current, right? It's going to be, mu naught n times I in a direction, by the way, that's parallel to the vector dA. It's along the axis of the solenoid. Because of that, this dot product that you're going to have between the B field and dA, simplifies, right? Let's do the simplification right in here. B parallel to dA, right? dA is pointing outside the solenoid, along the axis of the solenoid. So this B dot dA becomes B dA. Okay. B is mu naught Ni, is a uniform field, times dA. Everything here, oh, don't forget this I is a function of time. Function of time here. Function of time here. Right? Mu naught Ni doesn't depend on the position, so you can take everything out of the integral and put it outside. They are still, they must still be differentiated like that. But let's not forget that, oops, this mu naught and n, they are all independent of time, so you can take them out of the differential as well. Okay, and now we are left with this flux. This flux, remember, refers to the magnetic flux, not any other type of flux. And because it refers to the magnetic flux, this area refers to the area of the solenoid that the flux is going through. Let's take a look here. Our drawings right in here. We're calculating the electric field right in here, right? On the outside of the solenoid. The vector area is pointing towards you as well, so it's parallel to the magnetic field. So the area that we are talking about is going to be this area here, cross section of the solenoid. It doesn't extend all the way down because there is no magnetic field here. The magnetic field here is constant, the magnetic field here is zero. So there won't be any flux in this area that you see here. There will be a flux only here. Because of that, this area must be pi r squared. Okay? The only term that's time dependent is your current. I didn't put the time dependent of the current yet. But you saw right here this I max cosine of omega t, right? So now we can go ahead and put I max. Oops. Cosine omega t. I max can be taken out of here. And we go ahead and differentiate our cosine, which will result in omega here, and oh, strictly speaking, this differential is minus sign, so we end up with a plus sign here. Now we have an equation that's going to tell us what is the electric field, what's the induced electric field. Okay, so there are some simplifications that we can do. Pi cancels out with pi, and the 2r can go upstairs. Here you go. That's what we end up having. So that's the electric field. That's the induced electric field. That's the electric field induced by that changing magnetic flux. I'm going to put that right in here. Right. Notice that the faster the rate of change, the angular frequency, the bigger the amplitude of the induced electric field. Okay. Now, very important. Take a look at this dependence here on the distance. Very important. This field depends on the inverse of the distance. Let me remind you. Okay, we have an induced electric field, and I'm gonna specifically labeled here induced electric field. That's inversely proportional to the distance. Inversely proportional to the distance. And then we have a regular electric field of a point charge, right? Electric field of a point charge, what about PC? That is what? Proportional to the square of the distance. And then we also have, I'm going to be just PC here, an electric field of a dipole that's in proportional to the cube of the distance. Look what we have here. This induced field decreases much slower than this other field here and this other one. No? Notice that the induced field goes down with the inverse of the distance. Whereas the other field goes down much faster. So, if you were to choose, for instance, an electric field, if you were to use, not choose, but use an electric field to communicate with someone at a distance, you'd be better. You'd be better off choosing an induced field. And not the other ones. Okay, and that's exactly what we do, and that is exactly what we do. We do not use a point charge to communicate with one another. We do not use a dipole, a static dipole, electric dipole to communicate with each other. We use instead a changing magnetic field that induces an electric field which decreases with the inverse of the distance. We are far better off using something that decreases in magnitude far slower than the other ones, okay? I want to remind you that we did all this calculation, for R greater than big R. What about for R less than big R? For R less than big R. That's the second part of the problem. It's very similar, but the result is going to be different. The final result is going to be different. Okay? So what I'm going to do, I'm just going to copy and paste what I have right in here into the second part of our solution. Okay? We are going to need that. Okay? So, just like before, this problem has cylindrical symmetry. This problem has cylindrical symmetry. So we choose a circular path to solve our left side integral. Okay. And now that here you go. This is the other. Here you go. Now my path, the path that was chosen is the one here on the inside, right? The left side is not going to be any much different. We can choose a direction that path direction that coincides with the direction of the electric field. Okay, and because of that, this problem has a little symmetry, so we choose a path to solve our left side integral, right? We can choose choose a circular path, what else do we have to do? The direction of the path can be chosen to coincide with the direction of the E field. When we do that, we just have the same thing. I'm just repeating what's goes here in the left side is exactly the same thing that we did for the other problem. Okay. What's going to be here? EDL, right? EDL. Okay. The magnitude of E along the path, along the circular path, is the same. Is the same everywhere at that path. Consequently, we can take E here outside. Okay. And when we take the length of the entire path, it's going to be 2 pi r. And now we are left with this right side integral. What change is going to be this right side integral? Okay. Recall again the right side, the direction of the B field is going to be in the same direction of the vector area. So we will end up having something like that. Because we are talking about a solenoid, the magnetic field is going to be given by this expression, mu naught n I. I is a function of t. And you can take, because none of those terms is a function of x or y, right? We can take it out from the integral. And we are left now with this area, integral, the integral of this area, which, by the way, is going to be different from the previous problem, right? Why is that? Because it's going to be a smaller area. And don't forget, it's the area enclosed by this path. So this area here is going to be pi r squared, lowercase r. That's going to be the important difference that you're going to get. And instead of, r, big R squared, is going to be lowercase r squared. Mu naught and n can be taken out of the differential. Okay. And so pi r squared, they do not depend on time. Okay. The I of t is going to be I max cosine of omega t. We differentiate the cosine. Oh, let's fix that right here. It's going to be r, lowercase r. The cosine turns into sine with omega multiplied. The negative sign cancels out this other negative sign. And we still have, oh, don't forget this big R here, should be lowercase r. And now we can start simplifying. Pi r. The 2 here, I'm gonna emphasize that this r goes right in here. And I'm going to put the the two together with the other constants of the problem, okay, like that. And now what we get? We get that inside the solenoid, this electric field, this induced electric field, increases linearly with r and decreases with the inverse of the distance. So here you go, from here to the edge of the solenoid, the induced field increases linearly, and once outside the solenoid is going to decrease with the inverse of the distance. Okay? So that's the problem that we have for you. Okay, now we're going to talk about the generators, okay? And I'm going to use this illustration that you see right in here, okay? What you see here, edge on, is in reality a loop that you're looking side on, okay? So try to imagine your loop. This loop that you see right in here is essentially this loop that you see here in the other direction, looking along towards the z-axis, okay? So here you go. Look at the z and x axis here, okay? The y-axis coincides with the plane of the loop, okay? So here you go. Now we're looking straight into the z-axis. So what you see right in here is a loop like that, okay? At this very moment, the magnetic field is grazing the loop, and there is no magnetic flux whatsoever. And that's what you have here right now. The magnetic field is grazing the loop, and there is no magnetic flux whatsoever going through this loop. But what else do you have here? In the case of this loop, we also have a mechanical device that's making it rotate along this direction that you see right in here. Okay? In this other direction, the loop is rotating in the clockwise direction if you look straight into the y-axis. Okay? So if at this moment the magnetic flux is 0, since the loop is going to rotate a little angle, then we are going to start to have some magnetic flux going through this loop. So because of that, at this very moment in time, we can state that the derivative of the magnetic flux with respect to time is going to be greater than 0. Okay? And so the magnetic flux is increasing from 0 until a maximum value that you see right in here. Okay? Notice that I put my area vector oriented in such a way as to be parallel to the magnetic field. So try to envision that, okay? So what's happening? We have a mechanical device that making this loop rotate. Having said that, this mechanical device can be almost anything. It can be an internal combustion engine. It can be a turbine in a hydroelectric power plant. It can be a human hand that's cranking this thing up, okay? So because the flux is changing in time, what's going to happen? We are going to induce, this magnetic field is going to induce an electric current in this loop, in this circuit, okay? So here we go. At time t equal to 0, the flux is 0, but the derivative of the flux is not 0. Also, this device is rotated with a uniform velocity, uniform angular velocity. Okay? When the vector area lines up with the magnetic field, with the external magnetic field, we have maximum flux and 0 derivative of the flux. Okay? So, from t equal to 0 until here, this derivative is going to be positive. Okay, and is going to generate the current accordingly. And then what's going to happen now? Now, in the next instance of time, the magnetic flux is going to decrease. Okay? The magnetic flux is maximum, now is going to decrease in value. It's still greater than 0 because the A has a component that's pointing the same direction as the B. Okay? And when the magnetic flux decreases in time, then there will be a current generated in the appropriate direction according to Lenz's law. Okay, so here we go. Decreasing, decreasing, the flux is decreasing. Right end decreases to 0. It was positive here because the vector A still have a component parallel to the magnetic field, and it becomes 0 right in here. The magnetic flux becomes 0 right in here. Okay. Then, because the magnetic flux became 0, right? Now, the flux is going to increase again and is going to induce the current until we come to the initial point that we had. Okay, we do have a very nice simulation in the internet that I'm going to show to you. A simulation that simulates this device that you see right now. The name of this device is as a generator. As generator converts mechanical energy into electrical energy, which is the best type of energy that you want to have around. Here you go. This is a walterfend.de website. I'm providing you with the link for the simulation. It's pretty good. Okay. So what we have here, we have a mechanical device that making this loop rotate. This loop is a rigid body. It's a very simplified loop. It's showing just one loop, right? But it can have several in there. So what's happening here? Because this loop is rotating, don't forget, this loop is subjected to a magnetic field right here, produced by this device, right? Magnetic field, I'm turning off and turning on. Okay, turning off and turning on. So because we have a loop here that's rotating the magnetic field, this loop is subjected to a changing flux, magnetic flux. Because the magnetic flux is changing in time, then we have this inducing current induced in the device. Okay? And that's the direction of motion of the loop. If we accelerate this, now you can see that the voltage being measured, which is also associated with a current. Don't forget we have a resistor here, right? Changes as time goes by in a sinusoidal fashion. It changes in a sinusoidal fashion because the rotation is uniform. It's uniform rotation. That's how this device works. We have a mechanical energy input to the system, and this mechanical energy transforms it into electrical energy. All of that is explained in terms of Faraday's law. Okay? In a more quantitative fashion, we have the following. We start with the magnetic flux, with the equation for the magnetic flux. It's something like that. Okay. Let's not forget. I'm going to put a regular A here because the magnetic field, the area in the magnetic field doesn't change. The only thing that changes is the angle between them, right? So we're going to put like that. You know, have B and A, and you have the cosine of theta, which is nothing more, nothing less than the angle between the vector A and the magnetic field B. Okay, and again, going back to our drawing here, this is the angle between A and B, right? At the beginning, this angle is positive. Here goes this angle here. As time goes by, the angle keep on changing, right? That's what theta is all about. Because this is uniform rotation, this theta can be replaced by a constant omega, angular velocity omega. The B doesn't change, the A doesn't change. Okay. So now, what do you do next? We're doing that to understand how the generator works, right? Now, what we have to do, we have to take the derivative of the flux with respect to time. This derivative here. Okay, so the derivative with respect to time becomes something like that. Like that. And then, since both the magnetic field and the area doesn't change as time goes by, so you can take it out of this derivative. And we go ahead, take the sign here. Oh. If we want to find just the magnitude of electromotive force, we can ignore the negative sign that comes here, right? If you want just to find that. But let's not forget this is just the derivative. But let's not forget also that the electromotive force is minus this derivative of the flux. So the minus sign cancel out with the other one. And we end up with something like that. The electromotive force that changes as this changes in a sinusoidal fashion as time goes by. That's the type of electricity that you get from our utility company. So whatever you get from your wall there changes in a sinusoidal fashion according to this relation. Okay? That's how the generator works. We have generators there at the power plant, which transmit its energy through the power lines. Okay? There is a very interesting parallel, very interesting parallel between the generator and the electric motor. Okay, what one does, the other does in the opposite way. Okay, so I'm gonna, how do they work? Okay, we say that the electric motor and the generator are complementary devices. How does it work? In the case of the generator, we start with mechanical rotation. The input is mechanical rotation, the output is electric current. So it's mechanical energy and the output is electrical energy. But for the electric motor, it's exactly the opposite. In reality, those two devices are almost exactly the same. In the electric motor, we use electric energy and convert it into mechanical rotation. We said, and we did cover the electric motor before, right? In the same website that you see here, you can see a simulation of the electric motor as well. Let's take a look. Generator, direct electric motor, direct current electric motor, right? So look how the similarities of those two devices, right? I'm going to put them side by side so you can see new tab, and I'm going to get the generator as well. Okay? So I want you to appreciate that what we have here, the one in the left is the electric motor, the one in the right is the generator. Okay, we have a magnet, we have a loop, okay, and in both cases they are rotating in the magnetic field. The difference is that here we have a power supply, an electric current that's producing a rotational motion, whereas here we have an input of rotational motion that's producing an electric current. But the device is almost the same. Well, I'm gonna do something else too. Yeah, we're gonna leave this way. We're gonna leave this way. The only difference here is that we have what we call a commutator, okay? A commutator that makes the device to turn round and round. So that's what we have for this chapter, okay? So summarizing, let's summarize. Let us summarize here what we did. One, we introduced a new law, Faraday's law of electromagnetic induction. Faraday's law of electromagnetic induction. Okay, what does it state? This law states that a changing magnetic flux strictly induces an electric field, which can be used to power a current in a circuit and produce an electromotive force. A EMF force. Okay. This law allows us to build devices that can convert mechanical energy into electric energy. This device is called a generator, which is used in power plants throughout the world. Okay, so that's what we have for for today, and then we will meet again soon to cover other chapters. Okay, so see you soon. Bye bye.